In this lecture segment, we want to take a short look at the three basic historical computer language types. Okay, let's get started. Computer applications are written in one or more programming languages, of which there are three basic types. These are machine language, assembly language, and high-level language. These three language types represent the historical progression of programming languages over time. So although this topic represents a short computing history lesson, I think it's important that you have some understanding and background of how modern programming languages came to be. Let's begin with machine language. In the early days of programming, this was all that was available to programmers. As the old programmer joke goes, all we had were ones and zeros, and sometimes we didn't even have ones, so we had to use eyes. Machine language represents the native instruction set that a particular CPU has been designed to understand. All data and instructions in machine language are simply patterns of ones and zeros. Therefore, all machine language programs look like nothing but an endless stream of ones and zeros, which would probably look like gibberish to most of us. For this reason, machine language is frequently viewed using a hex dump of a program's instructions and data, which we'll see an example of in a moment. As you might imagine, machine language was and still is difficult to write, and it is most definitely not portable between computers. It's no longer frequently used directly for programming, but it's important to recognize that it is still always present at the lowest hardware or CPU level. So even though we don't directly program in machine language much anymore, recognize that it is still there way at the bottom-most hardware level, and it is still the only language that CPUs can directly consume. Here's an example of what machine language looks like. On the left, we can see what a sample hex dump might look like. I just found this out on the internet, and to be honest, I probably couldn't tell you anymore where I found this. If we take a look at this highlighted row of the hex dump, what this is telling us is that these 16 columns of hex data are the contents of the memory beginning at address hex 80, as seen here on the far left. How do we know that this is hex data? Well, if we look at some of these fields, we can see some F's and E's and A's, which is a pretty clear tip-off that this is hex data. Since each one hex digit represents 4 binary bits, we also know that each of these 2-character hex data fields represents 8 bits of memory data. On the right side, we can see the equivalent memory depiction of the shaded row of the hex dump on the left. As you might recall from a previous lecture module, this diagram represents the linear memory model. I drew this up in Excel myself for a bit more clarity. On the left, we see each of the 16 hex memory addresses clearly labeled, and in the middle are the binary equivalents of each of the pieces of hex data in the shaded row on the left. So for example, the first piece of data at hex 80 is 6F, which of course by a simple hex to binary table lookup is 0110 for 6 and 1111 for the F, and so forth for all the other hex dump cells. Although even this isn't the easiest thing to work with, just imagine for a moment how much more difficult it would be if all of this hex data was reverted back into the native ones and zeros of this machine language. A pretty nasty prospect, right? Before we leave this slide, I do want to make the important point that internal computer memory never sees this type of hexadecimal data, only this type of binary data. As we said previously, hex is for humans, but binary is for computers. So this on the right is what native machine language would look like to the CPU. So as we saw on the previous slide, working with machine language directly is not an appealing prospect for programming. And this is what led to the next evolutionary step up the computing ladder, assembly language. Assembly language allows the use of short CPU-specific mnemonics for individual instructions rather than ones and zeros. It also allows for the use of symbolic names for variables and their memory addresses. With assembly, special programs called assemblers turn programs written in assembly language into the equivalent low-level machine language. It's important to recognize that there's still a one-to-one correspondence between one line of assembly language and one machine language instruction. In this diagram, we can get an idea of the relationship between assembly and machine language. Where before we might have a machine language instruction in binary that looks like this, and I'm just making these up, its equivalent assembly language instruction might be JMP, which stands for jump to some other instruction. Still a little cryptic, sure, but still much preferable to raw ones and zeros. Again, there's a direct correspondence between these two, and assemblers translate the JMP into the equivalent ones and zeros. Assembly language is still not portable between CPUs, which means that the assembly language for one CPU cannot be understood by another CPU. Despite this, it's still far more preferable to program in assembly language than in machine language. As application programmers, we still would not prefer to program in assembly language, but there are circumstances in which assembly might be preferred. For example, in embedded systems programming, where optimization for high performance is often a must, developers there might prefer to program in assembly directly. If you're interested in the embedded system concentration, we do offer a class in assembly language programming here at Sierra, and that is CS39. Here's an example of an assembly language program. Again, this is something I found on the internet. I'm not exactly certain what this program does, but it's for the Motorola 6800 processor. At this point, you might want to open up the companion PDF slide and zoom in to have a closer look. On the right side of this program, we see the various assembly language instructions and their corresponding mnemonics. On the left side, we can see the specific memory locations for each instruction and the machine language hex equivalents for each instruction and its associated arguments or data. Again, I'm not familiar with the particulars of Motorola 6800 assembly language, but we can make some reasonable inferences. For example, the LDA instruction is probably some type of memory loading, while the JMP is probably a jump instruction, and the CMP is probably a compare instruction. Assembly is still a little challenging to program with, but I think we can agree that it's definitely a useful step up from machine language, right?